Okay, I started recording the class. So again, does anyone have any questions about what we were, saw yesterday in the class? Okay, so what I'll do here is I'll share my screen again, and we'll go to the notebook that we've been working on. This is section B, right? So there, and I'll say connect. Say here's the button, and that gets connected to the backend computer, the Google from Google. Okay, so again, I'll keep repeating this. These are text cells. We can write some information there, and these are the code cells. And each code cell you can run independently. So we have imported math library because we were using the tan hyperbolic function, which is in the math. Okay, so if you run this, this is simply a thing, and it won't run because we didn't say math.tanh. This tan hyperbolic function is available in math library. So we have to give the address to that. Say, okay, you go find this function in math library. The function name is tan hyperbolic, and you use it. You do that operation on this argument. That's what we are asking. And this will be, okay. So this did not run because I had to run that one first, and then I had run this one first. So it will print that. And then what we did was, um, instead of using a single value of time, we created an array, like a time array with the regular intervals of time, and we used it in the expression. And only other change we made is, uh, we instead of tan hyperbolic function in the math library, we used tan hyperbolic function in the NumPy library. With these two changes, we get an array of v and an array of t, like this t array. So if I printed them in a neat format, like a table, that at each time what is the velocity calculated according to the formula that we have, the analytical formula we have. Okay, that is that. And okay, so your B section. So I have not even shown you the plotting yet. Okay, so now, uh, any questions thus far? I think that's what we did in the last class. Any questions on that? Okay, now, um, if you look at this, we have several values of time, and at each of those time steps, at each of those instances of time, we have calculated using our analytical formula what would be the velocity of the bungee jumper. So at this time it's going to be this, at this time it's going to be this. Now the next thing is, see, this is the thing, uh, this is the problem, and this is the differential equation we got for that problem. How did we get the differential equation? We applied the Newton's second law of motion, rate of change of momentum of the body, or mass times acceleration of the body, is equal to the net forces acting on the body. The net forces are the weight, which is m times g acting downwards, minus and then the drag force. But the drag force, we have a minus sign because the drag force is opposing the motion. Since the bungee jumper is falling downwards, the drag is acting upwards. So, and then this is the equation. And by rearranging that, we got this equation. And the initial condition is at time t equal to 0. Okay, excuse me. Um, at time t equal to 0, because he's just jumping, right? At time t equal to 0, his velocity is 0. That is the initial condition. So this is a statement of the problem. This describes how the velocity changes. An initial condition is at time t equal to 0, his velocity is 0. With these conditions, we solved the equation. There was some mathematical tricks involved, but ultimately we got this equation. Okay, this is the equation we got. Okay, this looks like this. Okay, so at different times we calculated the velocity. We want to plot it. We want to generate a plot like this with the t on the x-axis and velocity on the y-axis. Okay, so how you could do that? Um, Here you are. So that is what we have done so far. You know, see, I told you the mathematical model. The different steps are understanding the physical okay, understanding the physical, the real problem, and applying the physics to it, and then you'll get an equation, and then you have to solve that equation, present the results. So we have solved the equation using a. I'm sorry. We solved that equation using some analytical method, but just presenting the results, we are using MATLAB here. We have this data. Any questions so far? Anyone? So we have, I think, the class strength is slowly improving. There's no questions here. See, if you have any questions, you can type in the chat also. Every now and then I'll be checking that. And we only have 10 students today. But I don't know how to deal with that. Um, okay. So any questions? Now, the second thing is when we use this modern programming languages like Python and MATLAB, they help us in both ways. See, the first thing is the computation has become very easy. See, we simply created an array, and in one shot, it found what the velocity is going to be at different times. That's neat, right? In one shot, it told us that how the velocity will change with time. And then uh, with 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 an equal level of ease, we can also generate a plot for this, and I'll show you how. Okay, now I'll for plotting, the function that we use for plotting is available in this library, matplotlib. Okay, dot pyplot as plt. Okay, that function, this library has the function that we want to use. So we are importing that, and then when we are importing that, we are telling the interpreter that from here on in this program, we want to call that library as PLT. Okay, we run that. Now remember the variable names. The variable names that we have here are T vector has the time data and the V vector has the velocity data. If you go through this loop, I think I tried to explain this loop to you yesterday. You remember the loop, right? We are doing for I in range 121, which means in this loop, as the loop is executed, each time the I value will be changing. The first time this loop executes, I will have a value of 0. Second time, it will have a value of 1, 2, 3, all the way till 120 it will go. So for each of them, I'm saying print T of I. I'm rounding it to 2 digits, that's the second story. But what I'm printing is T of I, meaning the ith element in the array T. So first time I equal to 0, so it will print the 0th element. Second time, second element. And similarly, I'm saying print that and some space, and then print ith element in vector V. So first time it goes, it will print first element in time array, space, and first element in velocity array. then second element in time array, the space, and second element in the V array. But when I'm printing them, before I'm printing them, I'm rounding off to the 2 decimal points. That's what the round function does. Okay, because if I print without this, it will print too many decimal points, which we don't need actually. That doesn't add anything to the value. Okay, so this is one way of presenting the results. This is a very valid way of presenting the results. But the point is, even though the results are correct, this is a valid way of presenting the results. This is not very revealing. Okay, by looking at the numbers, you can understand things, but you don't get the full grasp of what is happening. Okay, to be able to do that, no, if you want to look at no, it's always the case. If I give you a table of data, it'll take some time for you to understand what is going on. But that same table of data, if I convert it into a bar chart, okay, or a line graph, then it is more easy to understand. So that aspect of analysis is called visualization. We have a data, we have this data. How do you visualize it? How do you present it in a way so that it conveys uh, good insights into the problem by when you know which clearly provides insights into the analysis that you have done. So for that, I think I'm repeating again. MATLAB has built-in plotting functions or built-in visualization tools, which you can use to visualize the data. So the simplest of visualization techniques is a line plot. That's what you saw here. See, this is a line plot. A line plot for t variable versus v variable. Okay, velocity versus time. So we'll do that. And the simplest one we to do is I'll say PLT. PLT is an alias. Okay, is a nickname per se for this library matplotlib.pyplot. Okay, we called it PLT. That library has a function called plot. And the way to use this plot function is, see, as I'm typing, it's giving me help. The way to use this plot function is the arguments are, I can give you an X array, a Y array, and it will plot a function between, see, I give two arrays to this one. One array is T, one array is V. So I have created these arrays, right? See, here is the visualization of those two arrays. This is T array, and T array goes from 0 to 12, and V array goes from 0 to 59.79. Okay, now I'm saying plot this. This plot, what it does is it simply plots with T on X axis and V on Y axis. If I run it, you'll see what happens. Unfortunately, nothing happened. I think, did I not run this other one? Okay, I did not run anything yet. Okay, so here we run this NumPy. We imported the NumPy, and I have run this. So we have generated this one. Now that we have this V and T available in the memory, so all I have to do is run it. See, that is the plot we got. And like I said, see, X is the V, X is the time T. It changes from 0 to 12, and Y is the velocity, which is going from 0 to 6. Okay, so this is the most basic of the plots, a line plot. And you see how easy it is to generate. It was easy not only to calculate velocities at different points, it was also easy, using a software tool like this. Not only the task of calculating the values becomes easy, but also the task of presenting them neatly. Now look at that. Right away, you got nice plot. And when you look at the, here's what I'm telling. When you look at the data, you cannot draw a lot of conclusions from that. You know, it's hard to read a story from the numbers, but from the graph, I can make a nice description. Now, looking at this graph, I'll tell this story. I'll say, okay, initially the velocity is increasing linearly, and then the rate of increase is decreasing. You see, the slope is high here, and then the slope is decreasing, 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 and eventually the slope has become zero, meaning beyond this point, the velocity is not increasing anymore. There comes a point where the velocity stops changing. See, all this story I'm able to tell if I look at the graph. If I look at this, if you look at it up and down several times, maybe you'll come to the same conclusion. But it is not easy to see this pattern. It's not easy to see this kind of trend when you are just looking at the numbers. But when you look at a plot, that will enable you to understand the underlying pattern in the data. Any questions so far? Hello? So what we have done is, we have calculated them in arrays, and then I have opened yet another library. That library has a plot function which simply plots TNV, and we got this. Now, there is always ways to make it more beautiful. It's a very simple plot. In the least, you will need some labels on x-axis and y-axis. I'll tell you how to add them. To add an x label, you'll say plt dot x label, and then you give the string variable that you want to be the x label. So I'll say time in seconds. That will appear as x label now, and I'll say plt dot y label. Y label, I'll say velocity in meters per second. Okay, and then for the entire plot also we can give a title that's called plt dot title. Okay, title is, we'll say velocity versus time plot for the bungee jumper. Okay. See, isn't that a nice graph? Now we have everything. The graph says x-axis is time in seconds, y-axis is in velocity in meters per second, and the title of the graph is velocity versus time plot for bungee jumper. That's a nice, complete representation of the, see, in a systemic manner, I have taken you, if you've been coming to the classes regularly, I have taken you from understanding the real world problem, and then bringing in the physics of the problem, and then from this understanding and applying physics to it, we have come to an equation, and that equation turned out to be a differential equation. Then we solved the differential equation, we got an expression, analytical solution, and then using that equation, you have generated this plot, how the velocity will change with respect to time. So, sir, yes, please. I'm very happy, Pradyumna.
Sir, but yesterday I was tried, sir, in Jupyter notebook, sir.
Okay.
Yes, sir. Math that, yes, sir. Math that time hyperbolic, it was not. It will shows the syntax error, sir.
Okay.
I was typing math that 10 words of it, sir.
But okay, I'm very happy that you're coming with the question, Maruf, because it tells me that you actually tried to do it. Yes, let's yesterday you asked some question. I'll answer that, and then I'll get back to you. Are you joining us through a laptop?
Yes, sir. Okay. Some network problem is there in my area, sir. That is the problem, sir.
I see. I see. So later, I think later when I'm done with this problem here, I'll
Yes,
ask
sir.
you to share your screen. I'll look
Yes,
at
sir.
that and we'll see why it is giving an error.
Okay, sir.
You said you did it in Jupyter, right?
Yeah, yes, sir. Jupyter Notebook, sir. Yes, sir.
Okay. I'll look at it. I think after I finish what I'm going to say, we'll look
Okay,
at
sir.
it.
Okay, sir.
Okay. So
Okay, sir.
any questions on what we covered today?
No, sir. Nothing, sir.
Okay. Thank you, Maruf. So
Thank you.
see now compare this with the kind of problems that you're doing until now. See, all the problems are like this, right? But what we do is for a given value, for a given simple value. Okay. Who is showing me his what? Let me see. That's Maruf, is it? Okay, Maruf. We'll look at you later. Okay. Um, yes. See, generally in engineering, when you have problems and all, if a equation is like this, what you simply do is you plot one value of time and say velocity is this. Compare that to what you are able to do here. We're able to do not only for one time, but for a range of times, and we even plotted it, and we came up with a kind of insights onto how the velocity is changing. It is changing linearly first with a large velocity, with a large acceleration, and the rate of velocity change decreases, and then the velocity change become almost zero, and then it's not changing anymore. See, this kind of insights you are able to give if you can elegantly solve the problem using a software. And this you can this sort of analysis you could do for all the problems that you have done in other subjects till now. If you do, your imagination is your limit. For every problem, for all the equations you have solved in problems before, you can ask yourself, let me get more insights. For example, that beam problem, you always found what is the deflection at the tip of the cantilever. Instead of saying that, how does the deflection change from the base of the cantilever to the tip of the cantilever? If it is a simply supported beam, how is the deflection at different points? See, you can get nice curves for that, right? Now, that is one aspect that you can get the value of the dependent variable as a function of independent variable. For different values of independent variable, you can estimate the dependent variable in one go. That's very big advantage. On top of that, you can plot it also. That's even better. Now, the second thing, what Maruf was asking me yesterday was what how can we do it when what can be done when we have if you want to see what is the effect of mass, what happens to the solution when we change the mass. So I'll do this. What I'll do is I'll copy the same aspect, the same things, the same piece of code, and I'll add a new cell here. Okay. After this, I'm adding a new cell. Okay. Here, what we do is we'll put we'll change. Gravity and CD. We'll leave it alone. Okay. So I'll do for 5 different values of mass. I'll say for I in range 5. Okay. So I'll say mass equals to, we'll start at 30 kilos like a small kid, plus I times 10. Now, what did I tell you about for loop? The for loop executes a fixed number of times, and each time it iterates. See, what I'll do is I'll put everything else in loop. Okay. Uh, we'll indent it. If you remember Python, the way we figure out the scoping is by indenting it. See, I indented all those. I think I'll also indent. Okay, we'll add a plot also. So you know, all these lines are in the loop. How do I know? Because those are all offset. See, those are indented, offset from the base. See, two spaces. So if the next one, I know I'll write some other thing. PLT dot LE GE end. Okay. Now for this line, we came back to the original starting position. So this is outside the loop. Whatever is immediately following the for loop and is intended to a fixed indentation, we have to make sure that it's all indented to same, no, indented by the same amount to the left. So these are on the loop. These are all inside the loop. Uh, I don't think I want. I don't think I need this in the loop. This could stay outside because this doesn't change from iteration to iteration. Time is same always, right? Time is always 1 to 12, 0 to 12. Okay. So in each of these, first time this, see, these three statements are inside the loop, meaning these will be repeated 5 times because I said in range 5. And each time the loop executes, the I will carry a different variable. The first iteration, it will carry a value of 0. So if it is 0, then mass is 30 times 30 plus 0 times 10, which comes out to be 30. And it will solve the equation that way, and then it will plot it. Now, next time when it goes into the loop, I will have you a value of 1. So 30 plus I times 10 or 30 plus 1 times 10 is going to be 40. So in the next iteration, the mass is going to be 40. And then it will calculate the values of velocity for this new mass. And then it will plot it. So this is the loop which will generate 5 plots for 5 different masses. Okay. So we'll run it. See, and this is what we are understanding. Uh, I think this is the smallest mass. As you increase the mass, he is getting more and more terminal velocity. But this plot is okay, but we don't clearly see which one is which one. There is a way to add that one also. I'll tell you what. Uh, Let me add these ones. Okay, so now you know that each line corresponds to different mass. Each time we are going through, we are solving the problem for a different value of the parameter mass. But this in the plot, it is not clear which one is which. I'll say then I'll say velocity evolution or velocity change evolution for different masses of the bungee jumpers. Now, depending on the mass, how the velocity evolution changes, how that velocity variation happens, depending on the mass of the bungee jumper. That is the theme here. And I'll tell you how to add a label. The way to add a label is you can say label. There is a keyword equals. Then here you can give what is the label is. You'll say um, mass. I think I'm not sure if this will work, but I'll see mass plus or mass equals m plus kilograms. I think this works. So I think I'll tell you what this means. I'm creating. Okay, let me see if it will work. If you are in doubt, you can always try it. That's the nice thing with. Okay, so I think I have to say. char. No, I think string. Yes, str of m. This might work. Yeah. Okay. So that works. So what I'll do is this. See, what I'm doing is for each of them, I want to give a label, and for each of the different curves, the label will come like this: mass equal to 70 kilograms, mass equals to 50 kilograms. So what this is, I'm adding three strings. I'm adding a string called mass equals, and I'm converting the floating point number m into a string, and then another string called kilogram. By adding these three strings, I'm making a label. So this label here, after here, I'll say tag label, same thing, right? Tag equals this, and I'll say here, because so it's not required to do it this way, but it makes it clear. So each time the m value changes. So inside the loop, each time the loop is executing, the tag, the label we are giving to the plot changes because the m changes. Okay, and this legend thing that adds that. You understand? I think these two, again, this is all part of making the result presentable. So here's this. See, we have a nice legend here. Now we know which line corresponds to which value of the parameter mass. Okay, so here for all these, the drag coefficient is same. When you increase the mass, initial velocity is same for all until 2 seconds. They're all falling at about same velocity, but starting about 4 seconds, their velocities tend to differ. Okay, whichever is the lightest mass, lightest bungee jumper, his velocity is low. Whoever is the heaviest bungee jumper, his velocity is high. And this difference appears after the first 2 seconds. See, that's a nice story I'm telling, right? I'm looking at the plot and I'm giving you insights regarding what is happening, how it is happening, and things like that. Okay, if you're a little curious what happens beyond that, I'm also curious. So what I'll do is let's go to 15. Let's go to 15. And I'll say 151. Okay, so this is what happens when we are changing the mass as a, and as we are playing with the parameter mass. Now, same thing, we could play with the parameter CD also. That's other parameter, drag coefficient. Now, what happens? See, this is velocity evolution for different masses of the bungee jumpers. As the mass changes, how is the velocity changing? The similar thing we could do, and I'll copy this, Control C, same piece of code. I'll run it here. And now what I'll do is, mass is going to be constant. We'll not change it. We'll leave it alone. And this CD will change it. And then you'll have to think of reasonable range. So I think we'll increase it in multiples of 0.1, let's say 0.1. So
Hello,
what
sir.
happens is,
Sir?
what is it? Yes.
Sir, in notebook is also doing like this, sir. Lab is different for Jupyter notebook, sir. Hello.
Yes, Maruf, I think I didn't follow the question.
Yes.
What is that in Jupyter notebook? What is not possible?
Sir, and their different codes are there, na, sir. In Colab and Jupyter notebook is different codes are same, sir.
No. I think it is Python. Python is Python. Some features are different.
Yes,
It looks different, right? Jupyter, this interface all looks different.
yes, sir. Sir,
And
but I was typing, sir, V is equal to G into M by CD, CD square of 0.5 into NP into tan hyperbolic G into CD by M to 0.5 into T. I was typed in Jupyter, sir, but it was not showing it was showing syntax error, sir. Yesterday
okay.
also that is the
Sure. Maruf, I think, I'm almost done with what I'm doing. After this,
yes,
you
sir.
share your screen. We'll look into that.
Okay, sir.
Okay. So what I'm trying to do is now we'll do for different values of CD. So first time this loop executes, the CD value is 0.25, then it's going to be 0.35, 0.45, and that way it will keep increasing uh, all the way to 0.75 because we're doing 4 loops. Yeah, it'll go to 0.65. So we'll do that. Now I'll change the tag also because the labels here we're changing CD. So I'll say CD equals and then string of CD, and the units are I think kilogram per meter. Okay, that's it. See, isn't it nice? Now what we are doing is we are we are taking a 70 kilogram bungee jumper, and we're trying to see what happens if you alter the CD, if you change the CD for different values of CD, how the solution changes. I think this is not capital CD, this is small CD in this case. Okay. Okay. So this is the other plot. Now how, again, this is reverse. See, when the CD is small, the velocity is high. And as the CD is increasing, the velocity is decreasing. But again, that difference only becomes apparent after the first 2 seconds. In the first 2 seconds, when the body is going slow, the drag coefficient doesn't matter. For all of them, the velocity is similar. Irrespective of the drag coefficient, there is not much difference in the velocity evolution of these different cases for the first 2 seconds. But after that, the drag has a very large influence. Wherever the drag is very small, the velocity is high. But if the drag is increasing, the velocity is low. Okay. So this is what you could do. Still, I did not start the analytical. I did not yet start the numerical solution. This is all analytical part, but this is only an illustration of what you can do if you solve problems using computer programming. Any questions so far? Any questions? Okay, so I think what I'll do is we'll ask Maruf to share his screen, and we'll see. I think why he's finding it difficult to run the simple code here. Maruf, you there? Maruf, I think someone is saying something. Yes, that's Maruf. Okay, I think looks like he got disconnected again. Keeps complaining about the network problem. Okay, so in the meantime, maybe what I can do is I'll take the attendance. Give me 1 second. Okay, let me get the attendance. How many people are in the attendance today? Okay, I'll stop sharing. Probably that's not required. Is Maruf here?